Alright guys, in this video I'm going to be going over questions 2 through 16. Be sure to review all of the information in this PowerPoint, that way you get lots of practice with free body diagrams. Also note that questions 17 through 20 are homework, so do those on your own. An object has a mass of 25 kilograms, a tension of 50 newtons, and a friction force of 30 newtons are acting on it as shown. What is the resultant force? The weight and the force normal, this R, they cancel out. So there's no resultant force in the y direction. All that's left is a resultant force in the x direction. So I can do 50 newtons as my positive direction, choosing the positive x, plus a negative 30 newtons, negative 30 because it's in the opposite direction. And I'm left with the resultant force of 20 newtons. And you can denote this to the right. Okay, next up. Okay, practice problem number 3. An object has exactly two forces. F1 equals 50 newtons and F2 equals 30 newtons applied simultaneously to it. What is the resultant force's magnitude? So these vectors are perpendicular to each other, and I will translate this 50 newton vector such that the head of this 50 newton vector rests against the tail of the 30 newton vector, and you can see why the resultant force is up in this direction. So this looks like a classic right triangle. So to get the resultant force for perpendicular vectors, I need to do 50 squared plus 30 squared, and then I can take the square root of all that. Let's see, 50 squared plus 30 squared, raising that to the 1/2 power, and I get a resultant force of 58 newtons. All right, next up. Okay, so this problem is a continuation of practice problem 3. This time we want the resultant force's direction. So I need to see, with respect to the horizontal, what is this angle right here? We're solving for theta. I have a side that's adjacent to theta, and I have a side that's opposite to theta. Going through my trig function, SOHCAHTOA, I can use tangent. Tan theta equals the opposite side, which is 30 newtons, divided by the adjacent side, which is 50 newtons. So theta equals tan inverse, arctan. You'll do second tangent for this, of 3 divided by 5. I've just reduced the fraction. So if I go second tangent, making sure my calculator is in degrees, second tan, alpha tan for me, 3 divided by 5, and I get an angle of about 31, you can't really read that, an angle of about 31 degrees above the horizontal. Okay, next up. Okay, practice problem 5. We're going to draw and label all of the forces acting on an object which is at rest on an incline. Pardon the typo. We need to resolve all of the forces parallel to the ramp. This is a really important practice problem. It's one that most students struggle with, and it's not going to go away. You're going to have to deal with forces on an incline. So you need to maybe draw a bunch of ramps, draw an object like a block on the ramps, and just get used to resolving these vectors over and over again until it's like second nature. So the first thing we always draw is the force of gravity, the weight of the object. So I start by drawing a large arrow that points straight down to the center of the earth, from the center of the object to the center of the earth, and then I'm going to label this W or F sub G. IB does not care what you label it as long as you label it correctly. Now we have something called the normal force. The normal force is what prevents the object from going through the ramp. I should not have drawn it that large. Let me erase this. You see, it should be a little less than the force of gravity. So this is, oops, R, the normal force. If you labeled it F sub n, that would be fine too. Check it though. This normal force is what prevents the object from crashing through whatever surface it's on. The normal force, if the object is like on a horizontal, a flat surface, like if this ramp didn't exist and we were just on a flat plane, the force of gravity would be equal and opposite to the normal force. However, we're on an incline, so this normal force is equal and opposite to a component of gravity that gets resolved along the plane or along the ramp. So this normal force is equal and opposite to this component of gravity that I'm going to draw right here. This component of gravity is at an angle, the same angle as the incline. So this theta and this angle between the weight or the force of gravity and the force normal or the force that's opposite to the force normal, these are the same angles. You can do a series of geometric proofs if you want to prove this to yourself. I'm not going to waste time in doing that right now. So you should know that this resultant or this normal force here comes from this red vector that I'm going to label negative r, which is equal to w times cosine theta. The w is my hypotenuse. I have the hypotenuse, I have an angle, I have a side, this negative r that's adjacent to the angle. So this normal force comes from the force of gravity, is one of the components of the force of gravity. We also have a component of gravity that tries to send the object down the ramp. I'm going to label it purple here. This vector, which I can translate up here, is what is a component of gravity that attempts to accelerate the object down the ramp. So my weight, my force of gravity has been split. It's been split into this red vector that gives rise to the normal force, and it's been split into this purple vector that is actually parallel to the ramp, to the surface of the ramp. And this force, which I like to call F down the ramp, or the parallel component of weight parallel, is equal to W sine theta. W sine theta. This is what this force tries to accelerate the block down the ramp. And it would go down the ramp if there was no friction force to oppose this. So right now we have an object is at rest. So I will have then an opposing friction force which prevents this object from sliding down. So it's up here, F sub F, force of friction. And remember, oh wait, we haven't covered that yet. So force of friction, I have force of friction here. I have my force normal. I have this W sine theta, which is the force that is a force of gravity that tries to send the object down the ramp. I have the opposite of the resultant force, this component of gravity, and then I have the gravity itself. So you need to practice drawing a ramp, drawing an object on top of a ramp, and resolving these vectors over and over again until it's just like second nature. Okay, I'll see you for practice problem number 6. Okay, hopefully you reviewed the previous slides on friction. So practice problem number 6. A skydiver jumps from a plane and opens her parachute a few seconds later. Sketch a graph of her speed over time from the moment of jump to just before hitting the ground. So this is a very common question that IB likes to ask students. Do you know how to conceptualize speed? When dealing with these types of problems, when dealing with friction type problems. Okay, so I'm going to label speed V here, and here's my time axis. Please note that speed is a scalar, not a vector, so even though she's parachuting or she's going towards the ground, her speed remains positive. So she's jumping from a plane. The moment of jump, her speed is 0, and then her speed accelerates under the influence of gravity. So you can imagine suddenly the speed increases at a linear rate, Okay, and then it says she opens her parachute a few seconds later. So you can imagine at the moment she opens her parachute, suddenly her speed is going to slow. It is going to drop. It's almost like a discontinuous function. So I can just imagine her speed is suddenly going to crash but not go totally to 0. And then she will remain at a low speed until she eventually hits the ground, but they don't ask us to sketch that. So this is when this part is before parachute, before opening her parachute. This tip is the moment of opening the parachute. And then her speed decreases slowly. Her speed is going down until it becomes constant. The parachute prevents her from accelerating to the earth, but she still descends at a constant rate. And the reason her speed is constant is because the drag force of the parachute, F drag, matches the weight of the parachuter. Okay, so that's a constant speed. If you have a net force that's 0, just remember you can either have no velocity or you could be moving at a constant velocity. All right, I'll see you for practice problem number 7. Practice 7, a piece of wood with a coin on it is raised on one end until the coin just begins to slip. The angle the wood makes with the horizontal is 15 degrees. What is the coefficient of static friction? So let's draw our scenario. We have a ramp. I'm over-exaggerating the angle. The angle is 15 degrees, 1, 5. And I have a coin, which I'm going to just represent still as a block because that's really easy to draw. And let's start breaking these components, the forces acting on the coin into its components. So the first force we have is the force of gravity, the weight. Then I have the force normal, F sub n or R. And then I have this component of gravity that actually gives rise to the force normal. So this will be W cosine 15, because this theta matches the 15 degrees there, W cosine 15. I have this component of gravity that tries to send the object down the ramp, and I can redraw it up here. So this component of gravity is W sine of 15 degrees. And then, of course, I have the force of friction acting on the object, which is what holds it in place until I tip the object forward. So this force of friction is also equal to mu times the normal force, mu times F sub n. Okay, so I'm looking for the force of friction, and I know that this object is just beginning to slip. So I can say that the resultant force on the object at the moment of slippage is still 0. So my force of friction is going to be equal to the force trying to drive the object down the ramp. So I'm going to write this in black. The force of friction is just equal to the W sine of 15 degrees. Now, what else does force of friction equal? Force of friction also equals mu times force normal. So let me sub force of friction for mu times force normal. Mu times force normal equals W sine of 15 degrees. So far, so good. Now I can further replace my force normal with this W cosine of 15 degrees. I told you before that this force normal, what gives rise to the force normal, usually on a flat surface, is just the force of gravity. But in this case, because we're on an angled surface, we're on an incline, the component of gravity that gives rise to the force normal is W cosine 15. So I will replace the force normal with W cosine 15, and I'm going to write down here, mu times force normal is W cosine 15 equals W sine of 15 degrees. And I'm looking for mu. So I'm going to divide both sides by W cosine 15. If it's okay, I need space on this slide, so I'm going to erase. Please just write down or pause the video where I'm going to erase this part up here. Let's see, make some space, make some space. Okay, because now I'm just looking at the algebra. Okay, all right. Mu times W cosine 15 equals W sine of 15. So my mu then equals W sine of 15 degrees divided by W cosine of 15 degrees. My W's are going to cancel. And notice I have sine 15 degrees over cosine 15 degrees. This is a trig identity, and it's one you could easily prove to yourself by looking at SOHCAHTOA, but I'm just going to go ahead and state it for brevity. Sine theta divided by cosine theta equals tan theta. So this becomes tan of 15 degrees, and you can simplify to get your coefficient of friction. Mu equals tan of 15 degrees. Plug that into my calculator, second tan 15, and I get a coefficient of static friction of 0.267. I'll just round this up to 0.27, and it's a unitless number. The coefficient of friction, unitless. All right, I hope you didn't find that too challenging. You need to review this over and over and over again until it becomes like second nature. I'll see you for practice problem number 8. Okay, so in this practice problem 8, it's pretty much like number 7. Now suppose the plank of wood is long enough so that you can lower it to the point that the coin keeps slipping but no longer accelerates. So just like before, we have all of the forces on the object are canceled. So the resultant force, the net force in any direction acting on the object is 0. So if this new angle is 12 degrees, what is the coefficient of dynamic friction? So in this case, you always need to practice by drawing. So I have my ramp here set up with my object on top, and this angle is 12 degrees. We start by labeling the force of gravity, W sub g. We're going to label the normal force. This is R, or F sub n. We can label the force of gravity that gives rise to the normal force. This is W cosine of 12 degrees. We have the force of gravity that causes acceleration down the ramp. That is W sine of 12 degrees, which I can translate up here as well. I have my force of friction that prevents the object from accelerating. That's why the velocity is constant. The change in velocity is 0, so this is force of friction. And just like before, I'm going to say that the force of friction equals W sine theta. And I know that the force of friction is mu times force normal equals W sine theta. And hopefully, once again, you'll go through all the steps and you'll get that in this case, mu sub k, coefficient of kinetic friction or dynamic friction, is equal to tan of 12 degrees. I want to see all your steps. Be sure to show it. Follow me to practice problem number 9. Okay guys, for practice problem number 9, please note that this 25 kilograms, it should be 25 kilograms here also. And also this problem is pretty involved and I don't have a lot of space. I don't write very well with my stylus, so I'm going to make an additional video. I'll link the video in the PowerPoint just on solving this one, so the video will be linked. And I will link it on YouTube. Okay, so we're going to go on and do practice problem number 10. Okay, practice problem number 10. A 1,000-kilogram airplane is flying at a constant velocity of 125 meters per second. Label and determine the value of the weight, the lift, the drag, and the force, the thrust force, if the drag is 25,000 newtons. Okay, so let's label our forces. We have the big one, the weight, and the weight is equal to 1,000 kilograms times the acceleration of gravity. I'll just round that up to 10. So the weight is 10 to the 4 newtons. And this weight is equal and opposite to the lift. It's flying at a constant velocity. It's not going up or down. I hope it's not crashing to the earth. So the lift here is equal and opposite. L equals 10 to the 4 newtons of force. And then I have drag and I have thrust. So drag here goes out the back. That's like air resistance. The drag equals 25,000 newtons. And then the thrust force, this green F, what should that be? It flies at a constant velocity. Doesn't matter if it's constant 125 or constant 0. It's not accelerating. So the F thrust, F equals also 25,000 newtons. All right, let's go on to the next one. Okay, practice 11, a 1,000-kilogram airplane is flying in perfectly level flight. The drag D is 25,000 newtons and the thrust F is 40,000 newtons. Find its acceleration. So I have it's just like from before the plane. We have a thrust of 40,000 newtons, I guess heading east, and I have a drag force of 25,000 newtons. So according to Newton's law, this thing has a net force acting on it. This net force is 40,000, 40K minus 25K, which is equal to 15,000 newtons. So that is the resulting force, and it is to the right. My 40,000 newton magnitude vector is larger than the 25,000 newtons, so 15,000 newtons left over. So how do I get the acceleration? F net force equals the mass of the object times the acceleration, dividing both sides by m will give me the acceleration. So the acceleration of my 1,000-kilogram plane is 15,000 newtons divided by 1,000 kilograms. So 15 E3 over 1 E3 becomes 15 meters per second squared. Excuse me, let me write this like IB. Meters times seconds to the minus 2. And that's our answer. Okay, going on, practice 12. Okay, number 12, we're going to solve for acceleration. We have an object, has a mass of 25 kilograms, a tension of 50 newtons, and a friction force of 30 newtons are acting on it as shown. What is its acceleration? When I wrote this problem, I realized I don't like this problem. I'm going to rephrase it slightly. Let's just say there's a force of 30 newtons acting, and I'll just delete this friction part. So this 30 newtons is just like so. And give me its horizontal acceleration. Horizontal acceleration. And I'm sorry, there are complications when I think about how I phrase this problem. So we need to get the parallel component, the horizontal component of this 50 Newton force. No, and also, look, I forgot to tell you that the 50 newtons are at some angle. This was just not a good problem. So let's make this angle 45 degrees. So we're going to get the horizontal component of this 50 Newton vector. We'll do 50 times cosine 45 degrees. 50 times cosine 45. This is 35, around 35 newtons. So I just want the horizontal acceleration. 35 minus 30 gives me the net force, the net horizontal force, that's 5 newtons. The mass of the object is 25 kilograms, and from Newton's second law, F equals m times a. The acceleration is the net force divided by the mass. The net force is 5. The mass is 25 kilograms. 5 over 25 is 0.2 meters per second squared. Okay, practice problem 13. A 25 kilogram object has exactly two forces, F1, 40 newtons, and F2 is 30 newtons. And notice that F1 is at an angle of 25 degrees above the horizontal. What is the object's acceleration? So again, we're going to use Newton's second law that states that the net force on an object equals mass times acceleration. We have the mass, we need the net force. But notice that this F1 has a component of force in the x direction, the horizontal direction, and which is right here. And it has a component of force acting in the y direction, the vertical direction. So to get the net force, when we have forces acting in two dimensions, we need to do some Pythagorean theorem. In this case, F net equals the square root of my F net y, all of my vertical forces squared, plus F net x squared. So we're going to get the sum of all of the vertical vectors, and we'll get all of the horizontal vectors. We will square them, add them, take the square root, and that'll give me the net force. So I have two vertical vectors. This right here, the F2, is totally vertical, and then I have a vertical component of F1. The vertical component of F1, looking at the angle, this 40 newtons is like a hypotenuse, and I have a theta, 25 degrees, so Fy1 is what I'm going to call this vector right here, Fy1 equals 40, the hypotenuse, times sine of 25 degrees. Make sure your calculator is in degree mode. So I take the hypotenuse, 40, and I multiply by sine of the angle to get the opposite side to this for this vector triangle, and that gives me a value of 16.9 newtons. So I can get my F net y, my total forces in the y direction, and that's 16.9 plus 30. Which is 46.9 newtons. So now my F net y, I'll replace in this equation. It is 46.9, and I will end up squaring that. Now I need the net force in the x direction. That's this blue vector right here. So to get that, I need to use the cosine function. So let me make some space. F net x, there's only one force in the x direction. It's the horizontal component of F1. So this will become, this is an adjacent side to this angle. So I'll do the hypotenuse, the 40 newtons, times cosine of 25 degrees. 40 times cosine. 40 cos 25 degrees gives me 36.25, I'll round up, 36.3 newtons horizontal. 36.3, whoops. So now I'll plug that into this equation over here. 36.3. Okay, so I take 46.9, I square it. I add that to 36.3 and I square that. Then I raise all of that to the 1/2 power and I get a net force equal to 59.3 newtons. So let me draw this triangle, what this looks like. If I look at these vectors, my resulting vector triangle, this is what this looks like. My net force in the y direction is 46.9 newtons. I had a net force in the x direction, sorry the arrow's a little too large, but that's okay, 36.3 newtons. So my F net is the resulting hypotenuse of this vector right triangle. It's 59.3. Let's get an angle for this as well. We'll get the acceleration because we need the object's acceleration. It's the mass, it's the force divided by mass. F net equals mass times acceleration. So to get acceleration, I'll divide by mass on both sides. So in this case, I have 25 kilos. 59.3 divided by 25 kilograms gives me an acceleration of approximately 2.4 meters per second squared. If I wanted a direction for this acceleration or a direction for the net force, it would be this angle above the horizontal. So if you want, you can do that. We can use our tangent function. Tan inverse of opposite over adjacent. Tan inverse 46.9 divided by 36.3. And then you can figure out what this is. Okay, practice problem 14 up next. Okay, a 25 kilogram object resting on a frictionless incline is released as shown. What is its acceleration? So there's no friction acting on here. So let's go ahead and draw our free body diagram. We have the weight of the object, W, acting down. I have now this, I'll just still draw, it's good practice. This is my normal force. You'll see it as R, or you can label it as F sub n. No points off for either. We have this component of the weight that actually gives rise to that, which is Fg or W times cosine 30 degrees. And then we have the force that's parallel to the incline, and this is the component of gravity that actually accelerates the object down the ramp. So this component is weight, or Fg, weight times sine of 30 degrees. So I'm going to get the force, and I'm looking for acceleration. This W sine 30 degrees, because there's no friction, this is the net force acting on the object. There's no friction to oppose this. So the object is just going to accelerate down. So W is mass. W is mass. Okay, let me just write it like this to start. I'm not going to do it all in one fell swoop. Okay, so I'm going to say that the F net equals W times sine of 30 degrees. Okay, and I'm looking for the acceleration. So I know that acceleration equals F net divided by the object's mass. So I'll plug this W sine 30 in for F net, and I get acceleration equals mg, m, the mass, times g. So the mass times g is the weight. M times g is this weight. Times sine 30 degrees divided by the mass. And notice how mass cancels. So my acceleration is simply g times sine 30. You can use 10 for this, times sine of 30 degrees. Notice how it's just proportional to sine of the angle. This acceleration, I'm doing 10 times sine of 30 degrees. And I get 5 meters per second squared. Cool. Going on, practice 15. Okay, and so a 25 kilogram object resting on a frictionless incline is released as shown in the previous problem. What is its speed at the bottom? So for those of you who took physics before or know about the conservation of mechanical energy, I have no work loss to friction, so I can say that the potential energy, mgh, at the top will equal the kinetic energy, 1/2 mv squared, at the bottom. My masses cancel. Solve for your velocity at the bottom like that. For those of you who don't yet know about gravitational potential energy or conservation of energy, we're going to use SUVAT. So let me erase this, and I'll show you how to calculate this using SUVAT. We have the acceleration from the last problem. The acceleration of this object is 5 meters per second squared, and I know the object is starting from rest. Oops, sorry. I know the object is starting from rest, so initial velocity 0 meters per second. And I'm looking for V final, which means I either need the time it takes or I can solve for the displacement. So let's get the displacement of this object, knowing that my opposite side of my triangle of my ramp is 6 meters and my adjacent side, and my angle is 30 degrees. So I need this hypotenuse, which tells me the displacement of the object down the ramp. So I have a hypotenuse sine 30, sine of 30 degrees equals 6, which is the opposite side, divided by the displacement, s, down the ramp. So s equals 6 divided by sine 30 degrees. S equals 6 divided by sine 30. I'm plugging this in my calculator right now, and I get 12 meters. So I have acceleration, I have u, I'm looking for v, and I have s. I can use the Subat equation. V squared equals u squared plus 2 times a times s. V squared equals 2 times 5 times 12, 12. 10 times 12 is 120. V squared equals 120. Take the square root on both sides, or raise to the 1/2 power, same thing. 120 raised to the 0.5 power is around 11 meters per second. 11 meters per second. Okay, and let's see. If you did mgh equals mv squared, let's just check, as I like to do it. mgh equals 1/2 mv squared. Double check. So GH equals 1/2 V squared. 2GH equals V squared. 2 times 10 times 6 equals V squared. That is the same thing. 120 equals V squared. Cool. So either way, the math checks out. Moving on to practice problem number 16. All right, guys, practice problem 16, the last practice problem. We have a 100 Newton crate, that's the weight, is dragged across the floor by an applied friction force, F equals 60 newtons as shown. The coefficient of dynamic friction, I'm just going to put the coefficient of friction, is 0.60. Note it's unitless. What is the acceleration of the crate? Let us break this 60 Newton force into its horizontal component. So I'll take this green vector. The horizontal component of friction opposes the horizontal component of that 60 newtons opposes the force of friction. So this is 60 newtons times cosine of 30 degrees. This gives me a value for the horizontal force of 51.96. I'll round up to 52 newtons. The force of friction is mu times force normal. The force normal is equal to the weight. The magnitude of the force normal equals the weight. So force of friction equals mu times force normal. So that is 0.6 times 100, which is 60 newtons. 52 newtons of applied force is not enough to overcome 60 newtons of friction, so the object does not accelerate. Okay, I hope you found this video helpful. Thanks for watching.